Next up in our CLORPT equation is R for relief. Relief is basically topography. Topography is probably the word that you might be more familiar with. Topographic maps. People ask me why didn't they call it topography instead of relief, and I say clot is too hard to pronounce, so we have to have an R in there. So that's why we use the relief, but it's the same idea. It's the lay of the land, the shape of the land, how the ups and downs are happening and how they're relating to each other. So, a couple components, the main things that we're going to focus on: slope. How steep is the hill? Or is it just totally level? And second, aspect. If we have some slope, which direction is that slope facing? So, this is a little cartoon version of a hill slope model, and there are some terms that would be good for you to be familiar with. Summit is the top of a hill, right? I think that's a fairly familiar term. And then the rest of the terms are going to be related to body parts. We don't say the head of the hill, we say the summit, but everything else, we then slope off the summit, and where we start to slope is the shoulder. It's kind of this point where things are starting to increase in slope, and between the shoulder and the lower part of the hill, we've got kind of the steepest part. That is the back slope. So back slope, steepest part of the hill. As that slope starts to tail off, we see this starting to curve and lessen a little bit in the slope in this zone. That is our foot slope. And then the toe slope is essentially level at the very bottom of the hill. So summit, pretty close to level, toe slope, pretty level, and then we've got these 3 points in between going from starting to slope at the shoulder, steep on the back slope, starting to lessen on the foot slope, and then back to the toe slope. And this position on the hill is going to impact how the soil forms. And again, we're interacting with other factors here. It impacts a lot what happens with precipitation. We talked about slope as an element of effective precipitation. And runoff is going to be highest on the back slope, and run on is going to be highest on the foot slope and toe slope. So because of that, we expect sort of neutral development at the top of the hill on the summit. But then we have lessened development on the back slope. In part, we're losing water, so there's just less effective precipitation developing the soil. But we've got erosion, and so we're losing soil material, and so that's going to lessen development. And then at the bottom of the hill, we have accumulation of water and of sediment. In this image, you can see, get my pen back here. At the summit, we've got a reasonably well-developed soil. We've got some clay accumulation in the BT. On the back slope, so this is a back slope profile. The image is a little crowded. The back slope, we've got a BW. That's for weak development, right? We don't have the T fully developed, and it's a little shallower, thinner soil because we keep losing material. We have less water running through, and we have more soil getting eroded off the surface. And then down on the foot slope, toe slope position, in this case, this is just an almost undeveloped soil because there's been so much accumulation of material, of sediment, that there hasn't been time for pedogenesis, soil development, to happen. It's basically just keeps getting buried, and that burial is keeping it relatively undeveloped. Other models, like this one, usually the summit and back slope, we're kind of looking at similar moderate development, less development. Sometimes, though, we get even more development at the foot slope, depending on kind of that balance between how quickly are you burying it, or are you just kind of adding more water that's adding more development. So there are some complications. There's more going on than just one model, but generally speaking, we're losing stuff on the back slope and gaining it on our lower foot slope and toe slope positions. The other element of relief we'll focus on right now is aspect. So which direction is the slope facing? And this is maybe not an unusual photo for you to, you look at this and say, well, that kind of looks like an ordinary hill. In wetter parts of the world, you see less of this, but in relatively dry climates, we see a lot of trees on one side of the hill and less so on the other. And it's sort of a natural pattern. Even on this hill, there's kind of a greener patch over on here and then a much drier patch over there. This photo, it was taken in the northern hemisphere, and I can tell you that this way to the left is north. These are north-facing slopes. And that way is south. These are south-facing slopes. And the reason for that has to do with sun exposure. In the northern hemisphere, and I won't show you the southern hemisphere, but just flip it because that's how it works in terms of which direction the sun is coming from. Northern hemisphere north-facing slopes are getting less direct sunlight. The sun is usually a little bit to the south. It gets more and more to the south in the winter, and it comes up close to directly above in the summer at the solstice, depending where you're at in the hemisphere. But generally speaking, we're getting southern exposure. The southern-facing slopes are getting the sun, so the northern-facing slopes are a little protected, sheltered from the sun, so they're cooler. They have less evaporation, which means more effective precipitation. They have more plant growth because of that water, so more vegetation and trees, and those plants are impacting physical weathering and putting in organic matter. And so all of those things are pushing the soil toward greater development. North-facing slopes are a little cooler, so they're wetter and more developed. South-facing slopes, it's going to be the opposite, right? More direct sunlight, so more evaporation, less water working through the soil, less vegetation working on the soil, so less development. So not only does the vegetation look different, but we're going to have less developed soils on the drier looking parts of the landscape. Our final factor of soil formation that we'll talk about here is T for time. And time is the one truly independent factor of soil formation, right? Relief is modifying climate, and depending on your climate, you may have more erosion that will feed back and impact your relief. Organisms are interacting with climate. Parent material is maybe impacting what organisms will grow there, and that might impact microclimates, and how resistant the parent material is will affect how quickly it erodes and how steep your hill is, and so they're all kind of interacting, but time doesn't care. It's just, turns out it continues. Even if it doesn't feel like it this year, it has continued to pass one day at a time, and time basically just allows all of the other factors to happen. The longer the time, the more the other factors have acted on the soil. This chart, we're imagining one point in space, but watching it change over time as we move to the right. So at the very left, this is unweathered rock with basically nothing on it. We don't have soil yet, and then we get some plant growth, and those plants start to drop some litter. They're barely getting their roots down into tiny little cracks and start a little bit of physical breakdown, and so you start to get a little bit of sea material, broken rock that hasn't really altered yet, under that O, and eventually that sea material starts to get an A horizon building on top, where the plant roots have modified that sea material. The O horizon thickens over time, the A horizon thickens, we get subsurface development. We might get an E horizon depending on your climate, but likely to get a B horizon that first is going to be a BW and then maybe goes to a BT. Depends on a lot of other factors what the actual trajectory is, but the concept holds that more time, more development, more distinct and pronounced development of horizons. My one complaint with this figure, I've never seen a soil with an E and a BW. E's usually come in a bit after BTs, so that's me nitpicking a little bit. Other than that, the concept holds. Over time, things develop. This is from a study looking at 5 different locations, and they looked at soils in these different ecosystems, different parts of the world. Two of them in California, the San Joaquin Valley and the Sierra Nevada, but then compared to some other types of climates, and looked at young soils versus old soils. And this kind of gives you an idea of what we're talking about for scale. 10 to the third is a young soil. So 10 times 10 times 10,000 years, that's a pretty young soil. Up to 10 to the seventh, and then we're talking more than 1,000,000 years, that's very old soil. 10 to the sixth would be 1,000,000, right? So most of the soils don't get that old. 1,000,000 years is very old for soils. We're on a much longer time scale than human time, right? 1,000 years is young, 1,000,000 years is old, but it's a fairly short scale relative to geologic time. But over those times, in every system, we saw, so on our y-axis here, we saw clay increase. In some systems, it was a much more rapid increase. In Antarctica, we have some really old soils and not a whole lot of clay building up, but a little bit. There's a clay increase over time. It's a function of a bunch of other factors within that environment, but soils are clay factories. Over time, they produce clay. Weathering, physical weathering, and then chemical weathering, transformations produces clay. Depends on a bunch of other factors, but that's a pretty consistent feature of soil development. And one more image that I think shows kind of what I was talking about earlier. Time integrates our other four factors. All of those are kind of playing off each other and interacting and impacting each other, and all of that impact is happening over time. So time kind of integrates these other factors that are acting to develop the soil. All right, that sums up our 5 factors. I've got a couple review questions for you, and I'll talk through these ones, but I'll give you a chance to come up with your answer first. So, soil developing in an active floodplain in central China, silty alluvial soils that are somewhat poorly drained, climate is on the cool side, vegetative cover is mostly grass. So we've got, create that mental image. I've given you 4 options for horizon scenarios, right? So starting at the top, option A is we've got an O horizon on top of a C. Option B, an A over a B over a C. C, A, then E, then B, then C, or D, an A, and then a C. So which one of those horizon scenarios is most likely? First question is, are you going to have an O or an A? Because if it's going to be an O, we know that the first choice is right. Second question, are you going to have a B? And then the third question is, are you likely to have an E? So kind of how much development do you expect? Come up with your guess. And I'm sure you were right. My answer on this is D. And the reason I like D is because vegetative cover is mostly grasses. If we go back to our slide about plant communities and how they're impacting carbon in the soil, we said thick A's are common under grass. O's are more common in like a forest setting where you get that litter layer. So grasses, A, much more likely than an O. So we're going to rule out our O. The other piece of this is it's an active floodplain. So how old is this soil? Not, right? It's actively being added to. It's getting stuff dumped on it. We've got relatively cool climate that would suggest that we're not developing it super fast. And so we probably, if we are actively adding material to the soil, we're not a very old soil. This is a soil in the process of being deposited. So probably no B horizons. And definitely no E horizons. That takes a whole lot of time and leaching. And this is a young soil. It's an active floodplain. So D is our best answer on this one. Here's another one. Southeastern U.S. We've got a geologically old forested landscape, lots of precipitation, a well-drained soil. Similar question. Slightly different set of options. think it through. Pause if you need to. Once you've got an answer, hit play. First question, are we likely to have an O horizon? The fact that 3 of the choices have it and only 1 doesn't, that might make you think maybe not just the A, maybe an O is a good answer. But to check ourselves and not just rely on that rationale, it's a forested landscape. Forests, thin O horizons, pretty common, so that makes a lot of sense. Next question, so if we're starting with an O, then we've got some options with A's, with just a C, or with an A and a B. So the question is, how much did we get? Have we started an A? Have we added a B? And I would say, well, geologically old, lots of precipitation. Does that sound like a poorly developed soil or a well-developed soil? And in this case, that's definitely a scenario for a lot of development. So B is our best answer. Lots of time, lots of precipitation, forests, we've got organisms acting. There's plenty of soil formation going on here, so we expect a B horizon. Probably in that area, a BT, if we're going to get more specific. Soils are clay factories, and that kind of a setting is likely to get some clay accumulation. All right, so to recap, we wrapped up in this lecture material our last 3 factors of soil formation: organisms, relief, and time. If you have any lingering questions, please ask them. Office hours, discussions on Canvas, email, whatever you are able to do. Don't let your questions go unanswered, and we will see you next time.